So, welcome you all once again in this talk on theory of fixed point theory. So, as we have seen in the previous talks, the meaning of fixed point of a mapping from a metric space to itself, and then we have seen the definition of the contraction mapping, and we proved the Banach contraction theorem, which says that if the underlying metric space is complete and the mapping T from complete metric space to itself is contraction, then it has a unique fixed point. Okay, and now the thing is that if suppose we have T is not T is not contraction, but it is contractive. Contractive, you know that we have defined where we take the D of f T of x, f of y is strictly less than T D of x y. So that is called contractive. For example, if I'll write just the mapping T, you take from a metric space X to itself, and it is called contractive if D of Tx Ty is less than, strictly less than D of xy for all xy in X. Okay, so that is the we have mentioned that the T is contractive. But you see in the previous slides we have seen that here is we have mentioned that a contraction map, we have seen that the mapping T is contractive, but it is not contraction. In other words, we can see that every Lipschitz continuous function is continuous and every contraction map is contractive, but the converse is not true. This we have seen, and we can see that in the Banach contraction theorem, the space X is complete. Okay, and here is X is complete and T is contraction. Now the question is, what will happen if we consider T, the map T is contractive, not necessarily contraction? Will the Banach contraction fixed point theorem hold? That is to say, if X is your complete metric space and T is contractive, then T would have a fixed point. Now, you see, the important thing is that in the Banach contraction theorem, we are assuming only two things. One is the completeness of a metric space, and second is the mapping is contraction. Okay, so if we will relax something from the mapping, we will have to add something on the space. Only then we can do it. Because here you see, we can say, for example, so here is what we are doing. We are relaxing. Here is in this theorem, we are relaxing. We are taking T is your contractive map. So T is contractive map. Then we can see that then of course the T may not have a fixed point if X is only the complete metric space. But if we add something more, instead of complete, if we take X is a compact metric space. Okay, as we have seen that every compact metric space is sequentially compact and every sequentially compact metric space is complete. Okay, so compactness implies the completeness. Okay, so what we are doing, we are taking the mapping is contraction. So the contraction does not imply the contractivity, but contractive does not imply contraction, but contraction implies contractive. So what we are doing, we are relaxing something over here, but here we will have to add something more. Instead, that is to say, if we take X is complete metric space, then this result may not hold. So because we have relaxed the condition on the mapping T, so we added something here on the space X. That is, we are taking little stronger assumption than the completeness, which is known as the compact metric space. So X is a compact metric space and T is a contractive mapping, then T has a unique fixed point. So that is the important thing. And not only this, we can also calculate the unique fixed point. So we can take for any x. So suppose x is the fixed point, then this fixed point would be the limit of t and x. So we can start from x, we can take t of x, and then we can operate n times over t and take the limit as n tends to infinity. That would be the limit of this would be equal to the fixed point of map T. This that is the successive iteration. So first we can start from any x, we get t of x, and then operate again t over here, we will get t square x, operate again and continue in this way, you will get t n x, and so on. And then we will see that this sequence converges to the unique fixed point x bar of t. So let us prove this one. Of course, the proof is different than the proof of the Banach contraction theorem. So what we will do here is we first define a mapping psi from x to r plus, that is close interval 0 to infinity, by psi of x dx tx for all x is in x. Now, since dx tx, because this is d is a metric, so this is a real number and it must be greater than or equal to 0. And therefore, and of course, as we have, so this is greater than 0, and now we can see that this psi is a continuous function. So this we can see that this psi is a continuous function. So we take psi of x minus psi of y, okay, is equal to, by the definition, we can put the value of psi of x from here over this one and psi of y. So you took dy dt of y. And now you subtract this term and add this term and apply the triangular inequality. Then from here we will get this inequality. Now look here, what is this? This is your t of d of x. So this is by this is less than or equal to b. This is the dx tx minus dtxy. So this is less than or equal to dxy, and this is less than or equal to dtxty. And now we use the contractivity of t. So this dxy plus strictly less than dxy. So this is whole thing is less than, strictly less than 2dxy. So if we choose, so for a given epsilon, okay, let epsilon be given, then what we can say that the psi mod of psi of x minus psi of y is less than, from here, 2 times dxy. So this is less than epsilon. So this is less than epsilon whenever dxy is less than delta, which is equal to epsilon by 2. And therefore, and now, so we can see that psi is continuous. Now again, psi is bounded below, as I have already told you that because this is greater than or equal to 0. So the value of psi of x cannot go beyond 0, and therefore psi is bounded below. And now since x is compact, so x is compact, psi is bounded below and continuous, and therefore there exists a minimizer x bar of psi. Okay, that is to say there exists x bar in x such that psi of x bar is less than or equal to psi of y for all y in x. Now we will show that this minimizer of this function psi is nothing but it is a fixed point of t. So this we will prove that it is a fixed point of t. Suppose contrary that x bar is not a fixed point of t. Okay, then of course tx bar should not be equal to x bar.